So maybe the next stage that we look at here is differential equations that look like this. What's the big difference with that? There's a y involved there, right? Now you can have that, right? It says the slope is equal to that, right? The x divided by y, and then change the sign, right? Negative x over y. The good thing is for slope fields, for drawing a slope field, it's not really any different. It's not any harder or anything like that. We'll look at how to solve it algebraically in a second, but first we're going to draw a slope field for it to see what the solution curves might look like. You know how when you had a differential equation like this, dy dx equals x, for instance, you could right away say, well, I know the solution. It's negative, or it's a half x squared plus some constant. You could see right away that it's a parabola, right? It's not so obvious what the solution here is going to be. So we're going to draw the slope field first and then use that to get a sense of what they might look like. If you're drawing a slope field here, dy dx equals negative x over y. Everywhere that you're going to draw a little line here, you have to take the x-coordinate divided by the y-coordinate and change the sign. So I'm going to go about this in a kind of logical way here. I don't know if you want to try doing this first, or if you, let's say this point right here, because this is a pretty easy one to do. If I take the x and the y-coordinate for that point, x is 1, y is 1. So when I divide them, what do I have? I have 1, and then it's make it negative, so negative 1, right? The slope here is going to be negative 1. For the same reason, if I go over to this point, I got negative 1 and positive 1. So I've got, what do I have there? I have negative 1 over 1, but then make it negative. That's positive 1, right? So as you, for all of these things, try and use kind of, what you know about points. I wouldn't do one row like I did, or one column like I did in the other one. I would do some related points. The next 2 points I would do would be those points, because I know that it's all ones involved here, right? This is 1, negative 1, 1 over negative 1 and make it negative, 1 over negative 1 and make it negative. So this is positive 1. This is going to be negative 1. I would do some similar points here. What about if I pick points where the x and the y coordinate are always the same? Like, good ones to do would be these ones first, or all together, because it's always going to be the same there, right? Because everywhere there it's going to be 1 over 1, 2 over 2, 3 over 3. What's the slope going to be for all of those points? Negative 1, right? So I'm going to plot all of those. These are all negative 1s. And then probably the next place to go is here. What's the slope going to be everywhere there? Positive 1. So if we put a positive 1 for all of those, and then maybe let's pick some other related ones. Let's pick, say this, because this is actually pretty easy if you think about it. Everywhere there, well, you have 0 over something, right? Because the x-coordinate's always 0. So you got negative 0 over something. What's the slope always going to be there? 0. So I'm going to put 0 for all of these here. Now the middle, I'm not going to put anything for reasons that might be clear in a second here. What about if I look at these points here? It's x over 0. Normally on a slope field, you don't put anything if it's undefined like that. Dividing by 0 is undefined. You'll see when we kind of get a sense of what the curves are that it's just vertical lines. So I know some of you really would be tempted to put vertical lines here, but you don't necessarily know right off the bat whether it's going to be that. And usually on a slope field, you don't draw lines, even though you might know that they're vertical. So I'm going to leave those off of there for now. Everywhere else to fill this out, let's look at this point here. What's the slope there? It's 2 over 1 and make it negative, so it's negative 2. And then that means this has to be positive 2. And this has to be negative 2, and that has to be positive 2. And what about this point right here? What's it going to be? Negative a half, so we'll draw that. This has to be positive a half, and then we have negative a half, positive a half, and you fill them out, all the rest of them there. If you were to go through and fill out the rest of them, you're going to get things like 1/3, 2/3, and so on, right? This is going to be, or this is going to be -3. This is going to be -1/3. This is going to be -3/2. This is going to be -2/3. And you can fill the rest of them out the same way. This one is this one down here. Matches that one up above. 2/3, 3/2, 3/2, 2/3, 1/3, 3, and so on, right? Okay, so there's your slope field. Even though we haven't gone through and solved it algebraically, it's pretty clear what the solution curves are going to be from that, right? What are the solution curves going to be? Circles, right? They're going to be circles. Okay, so circles that are centered at the origin. So again, that's how a slope field is helpful. I'm not saying you're always going to, generate them by hand. Obviously, as I showed you, the thing online, there's tons of things you can generate them quickly. This gives you a graphical confirmation for when you solve it, or at least now it gives us a sense of, if we try to solve this algebraically, how we're going to get it to end up being what we want it to be. Okay. So we're going to try and solve it algebraically here. When you have two variables involved, you have to, if you can solve it algebraically, one way is to separate the variables. So this is what I mean by that. So that's this second part here says, see if we can solve this thing by separating the variables. So we had dy dx equals -x/y. If you want to solve that algebraically, you have to be able to separate the variables. There's slightly different ways to think about this. The way I think about this is, if I can put everything that has to do with y on one side and everything that has to do with x on the other side, like this is divided by y here, so couldn't I write this as y dy dx equals -x? Does that make sense? You could times both sides by y, right? Like, you have to know that y is not equal to 0, I guess, to make that work, but I could do that, right? Now, there's two different ways to think about this, but you can think about these two things separately, this dy and this dx. If you think about the dy and the dx separately as two separate, what you call differentials, I could write the dx on that side, right? If you think about that as a ratio of differentials, if you think about this as a ratio of kind of like change in y, change in x if you made it infinitely small, do you see how this could come from this? All right. If you're okay with that, then how you can proceed from here is you can integrate both sides. You can take the indefinite integral of both sides, as in, I'm going to put this symbol on both sides. I'm going to say integral of that side is the same as the integral of this side. I'm going to put it in there just to leave the negative sign out. We haven't talked actually formally about indefinite integrals yet. We've talked about definite integrals. Like we've said the integral from 1 to 4 of 2x dx. And you guys said, well, that's x squared evaluated for 4 and 1. The indefinite integral, which we'll talk about formally later on, is the integral of 2x dx is just what function has that as its derivative? What are all the functions that are possible? Well, it's x squared plus some constant. Okay? That's the indefinite integral of 2x. You guys already know this, even though we haven't formally talked about it. Now, just like you can talk about the indefinite integral, you can use integration on both sides of an equation. You can integrate both sides, just like before we took the derivative of both sides. When we did implicit differentiation, we had some kind of relationship, and we took the derivative of both sides. Here you can take the integral of both sides. Now, I am going to put this over here because I'm running out of space. Maybe that's a bad idea. Maybe I should do the old, just move this up and use the space underneath here. Hopefully you're writing smaller than I am. I have the capacity to add space here. if you looked at this, what function has y as its derivative if y is the variable? Because that's what that says. That says, tell me what function has y as its derivative if y is the variable. What would it be? A half y squared plus some constant. I'm going to put constant number 1 here because I'm going to need a constant number 2 on the other side. What function has x as its derivative? I got the negative sign outside there because you can leave it out there. I could have done this way, but you would just be ignoring that negative sign anyways. So I'm going to just leave that negative sign outside here. What function has x as its derivative? Half x squared plus c. I'm going to put c2 here. Now, when you're doing this, you don't actually have to put two constants because whatever those two constants are, what could you do with them? You could combine them together, right? If this was plus 2 and this was plus 7, you could just say, let's call it plus 5 here. So just to keep it simpler, what you might want to do is say, just say, I'm going to add a constant to one side and not bother adding a constant to the other side because you don't need to. And it doesn't matter which side you put it on because it could be anything. All right? So maybe you'll feel more comfortable if it's on this side. Resort to your grade 8 things where you think the number has to be on the right side and the other stuff has to be on the left side. Now, I'm not sure how familiar you are with the equation of a circle. We expect it to be a circle. I'm going to put this on the other side. So I'm going to make it say a half x squared plus a half y squared equals some constant. And just to simplify it here, since this could be any number you want anyways, and these both have a half here, what if I times everything by 2? What would I get? On this side, I would get it a lot simpler, right? I would have x squared plus y squared equals... Now, this thing, any number times 2 is still just any number, so I'm going to leave it as this. If you feel uncomfortable saying constant times 2 is constant, you could call this constant number 1 and then just call that constant. It's acceptable to just say, yeah, I'm just going to use c every time I have any number because it still represents the same thing. This is any possible number, and this is still just any possible number, so it's okay to use the same symbol there. Does this look like what you expected it to? That's the equation of a circle, right? X squared plus y squared equals something, all right? If you wanted to solve it with with some initial condition, which I think, did I give you an initial condition up there? I did, right? If you want to solve it with this initial condition, let's go back to the slope field before we do it algebraically. The solution that passes through 0, negative 2, this point right here, what is that going to be? The solution that passes through 0, negative 2? It's going to be I can't draw it very well, but it's going to be a circle that has a radius of 2, right? That might look almost like a circle, all right? That's the particular solution that passes through 0, negative 2. If we solve that, then what should we find is the value of that constant? Should be 4, right? Because that should be the radius squared. If you sub the numbers in, obviously it's going to work, right? 0 squared plus negative 2 squared equals our constant. Our constant is 4. So the specific solution that passes through that point is x squared plus y squared equals 4. The general solution, if we didn't have that initial condition, is just x squared plus y squared equals c. All right? There's one last thing in this section now that I hope you have a good understanding of slope fields, differential equations, and stuff like that. The last example here is, I wanted to give you this as a kind of a discovery thing, but if you read the title, it kind of tells you, this, if you try and solve it algebraically, you might run into some trouble. I thought, well, maybe I won't make the title where it gives away that, but this one's one where you can't separate it. To be able to separate it, you have to be able to write it as the product of two different things. Like the one we had before, dy dx was negative x over y. You could write this as negative x times 1 over y. Like you could write it as the product of two functions, one of x and one of y. To be able to separate the variables, you have to be able to write it as the product of something. Now, try as you might, you're not going to be able to write that as the product of two functions where one only has x and one only has y. But that doesn't mean you can't draw a slope field. It's just as easy to draw a slope field for ones that are not separable. And that's actually where slope fields are most useful, is for ones where you can't actually solve it algebraically. And the only way you can get a sense of what the solution curves look like is to create a slope field. Okay? So what I want you to try now is create a slope field for that. Just by, again, thinking about it the same way. Derivative is take the x-coordinate minus the y-coordinate. Plot the lines. Okay? Try to look for places where that's going to, like, instead of just picking random points, look for where it's going to be the same. It's a lot quicker that way, right? Where is this going to be 1? Put them all, make them all 1. Where is that going to be 0? That's why it says, where is this 0? Start by looking at where it's going to be 0. That's probably the easiest. Plot all those lines. Okay? So you hear that example right now. So hopefully you managed to draw something. I think it's easiest to try and look for where it's going to be, easy to draw the line. That's why I said where is the slope 0. The slope's going to be 0 when x equals y, right? So when x equals y, it's this along here, right? So anywhere along there, the slope's going to be 0. So you can draw lines here. I should be using a ruler to really make this clear. What do we know about this row right here? It's all positive 1 because x is 1 bigger than y. So this is going to be, this one actually I really should use a ruler to make my life simpler, but you have that, each of these. What is it going to be after that? It's going to be 2, right? And then it's going to be 3. Again, it's hard to, whoops, missed one. It's going to be 3, and then 4, and then 5, right? 6. It's hard to tell the difference between those. What's it going to be on the other side here? Right there. Sort of the opposite, right? That's going to be -1, right? So you have a little short line here like this. And then it's going to be -2, and we'll try to, complete this as quick as possible. And then -3. So even though this thing, okay, so I obviously did that pretty quickly, but it gives you a sense of what the solution curves look like. Now, who knows what this is going to look like? If you, it's different in one aspect here because of this. If I try to draw, this thing right here, if I try to draw a specific solution somewhere, if I draw this specific solution, let's say, did I have a point down here that goes through a certain point, passes through 0, 1. Is that what I said? Yeah, passes through 0, 1. 0, 1 is right here. It looks like it's going to go something like this. I have no idea, but it actually is going to, the closer you go there, it's going to be asymptotic like that. This is actually an asymptote, right? The fact that these are all straight into each other. If you drew the solution curve there, it'll be just straight like that. But if you draw any other solution curve, it's going to just get closer and closer, but those lines are never going to say you went through here if you drew one there. Now, we don't have enough lines there to see, but it's just going to get closer and closer, but never touch that thing. All right? So, one last time here. The fact that you can still draw the solution curve, even though you can't actually solve this algebraically, right? Because if you try to solve that algebraically, I'll do that down here, explaining why, right? If you have dy dx equals x minus y, You can't express that as a product of two functions. You can't separate it. You can try and move this y over to the other side, but you're going to get y plus something. Try as you might, you can't separate those things and then integrate each side. All right? So that is a look at separable differential equations, and then one last one that is one you can't separate. All right?